Okay, thank you, Sanjay, for the introduction. And let me first thank the organizers for inviting me to give a series of 2 talks. And though it's not possible to cover everything in these 2 talks, if you want to read in details about these neutrinos and their interaction in matter, then this is a review article published last year, Particle and Nuclear Progress in Particle and Nuclear Physics. This is almost 200 pages article. There you will find everything about neutrinos and their interactions with matter. What I will do, I will stick to the basics. I will try to let you know what's the interaction, how do we write the Lagrangian, then using the Lagrangian, how one writes the transition matrix element, and then how one reaches to the cross section, and then why the cross sections are important, where do they play a role, and then what are the different contributions of the different reactions channel, and why it is challenging to understand neutrino nucleon and neutrino nucleus cross sections. I don't know whether I will get time to talk about neutrino nucleus interactions, but I will try to cover a few points. But before talking about neutrino interactions, I will also talk about electron-muon scattering, because that is mediated by a photon, and that is much simpler than when we will go to neutrino-electron scattering, or we will go to the neutrino-nucleon scattering. While talking about neutrino-nucleon scattering, we shall talk about the quasi-elastic scattering, meson production like pion production, kaon production, eta production, associated particle production, and many others. Then deep elastic scattering and quark-hadron duality. Now, what we know in the standard model of particle physics, that there are 3 generations of leptons and 3 generations of quarks, but these we have independent electron family, muon family, and tauon family, where we have to take care of the lepton number conservation independently for each family. And then we have seen in the morning lecture that there are various sources of neutrinos, starting from cosmic neutrino background to Big Bang nucleosynthesis, then solar neutrinos, geoneutrinos, atmospheric neutrinos, and cosmogenic neutrinos. And really it is from, this spectrum is from micro electron volt to hexa electron volt. While in my talk I will stick to neutrinos of few hundreds MeV to a few GeV, where most of the accelerator experiments like NOVA, T2K, or the planned Dune experiment, as well as atmospheric neutrino experiments which are being performed. Now, why study of neutrino interaction is important? This is because neutrino is a fundamental particle in the standard model of particle physics. We can gain insights into the fundamental building blocks of the universe. Now, since neutrinos are weakly interacting particle, where it has been discussed that we have in the weak interaction the contribution from the vector part as well as the axial vector part. We have the vector contribution in the electromagnetic interaction, but here there is an additional contribution from axial vector part. Therefore, as a probe to nucleon axial vector response, the neutrino reaction is unique in hadron physics. The other important point is that neutrinos are produced in a variety of astrophysical processes, such as there cannot be any star in the universe if there are no neutrinos. And if we believe in the elements which is generally shown by the chemistry people, except for the transuranic elements, all the elements that we talk about, starting from carbon, oxygen, calcium, iron, uranium, thorium, whatever you talk about, either they have been produced in the star's core or during the S process, R process, etc. in the during the death phase of the stars, and therefore it is important. Then there is another point, that we are living in a matter-dominated universe, while at the time of Big Bang, where we had equal amount of matter and antimatter, and matter dominated. We want to understand that why is so, and therefore we want to understand CP violation in the lepton sector. We can understand why there is more matter than antimatter in the universe, then studying neutrino interaction can help us to understand their properties like their masses, mixing angles, oscillation behavior, and other things. Besides that, we had the talk on the detectors. Then innovation in particle detectors developed for neutrino experiments can be applied to medical imaging or national security or many other purposes. Now, when we talk about neutrino oscillation, events, etc., that means we talk about the neutrino detection. In fact, never a neutrino is observed. When we talk about helicity of neutrino, we never see a neutrino. What we see is the final state photon. And from there we infer that what is the helicity of neutrino. Similarly here, we observe the final state particles. And from there we say that whether an electron type neutrino had interacted or muon type neutrino had interacted. And almost all the detectors that we talk about, they are using moderate to heavy nuclear targets. Like if you talk about superconductor detector, there is using water-shed target. Or if you talk about the future dune detector, where argon is planned to be used. Therefore, you are using nuclear targets where nucleons are bound. And then nuclear medium effects become important. And the nuclear medium effects for the different processes that we talk about, whether it is quasi-elastic scattering, whether it is inelastic scattering, or the deep elastic scattering. These nuclear medium effects are different. Therefore, we have to understand the nuclear medium effects for all these processes separately. And that is a big challenge, to understand nuclear medium effects in neutrino nucleus reaction. And then it is important in the determination of backgrounds, reduction of systematic errors, because when we talk about precision neutrino physics in the oscillation experiments, then presently the systematics are large. And to reduce those systematics, we need a good understanding of neutrino nucleon and neutrino nucleus interaction cross sections, because it has been estimated that almost 25 to 30% uncertainty in systematics arise due to the lack in the understanding of neutrino nucleon and neutrino nucleus interaction cross sections. And that is why we have the NISER board and new series of conferences where we discuss about the neutrino interactions with nuclear targets. And for precision, we need around 1 to 5% in cross sections studies, the precision. Then when we talk about the near detectors and the far detectors in the neutrino experiments, like you talk about the NOVA experiment, or you talk about the T2K experiments, generally first it was thought that you will have direct cancellation of the uncertainties. But while the problem is with the different fluxes, with different flavor composition, different geometry, acceptance, and targets. Therefore, there is not exact cancellation, and therefore you have to understand the neutrino interaction cross sections. And what is more important, that the neutrinos are the most abundant particles after photons, but they are least understood. We are trying to understand this elusive particle, but not much has been understood. And why this has happened? Because the neutrino interaction cross section is typically very small. If I say that if there is a given volume, and if I am talking about an electromagnetic interaction taking place here, where we have a target particle. Now, if we want to understand, or we want to have the same interaction through weak interaction channel via a neutrino beam, then instead of one particle, I will have to put 100 millions of particles. And that is why the neutrino experiments are very challenging. Now, when we talk about the fundamental interactions in standard model, we have strong interactions, electromagnetic interactions, and weak interaction. Typically, the strong interaction cross-section is of the order of bonds to 10 power minus 26 centimeters squared. Electromagnetic interaction is 10 power minus 30 to minus 32 centimeters squared, while weak interaction cross-section is around 10 power minus 38 to 10 power minus 41 centimeters squared. Now the question arises, why this cross section is low? And what I have done, I have simply using Feynman diagrams, I have tried to explain in simple words from where these differences are coming. And as you can see here on the left hand side, I'm showing electron muon scattering, where electron muon is in the final state and electron muon is in the initial state as well as in the final state, while here I'm talking about neutrino electron scattering. Now this scattering will take place via electromagnetic interaction as well as via weak interaction through Z0 exchange. But nobody here talks about Z0 exchange, because Z0 means we are talking about weak interaction, and that weak interaction cross section will be much smaller than the electromagnetic interaction cross section. If you look at these two vortices, then here we have a coupling strength E. The nature of interaction is the vector interaction gamma mu, and then we have a photon propagator that is proportional to 1 over q square. And this E is related to the fine structure constant, and this number is here. While here, if you look at this, we had a small g, and then since this is a weak interaction, which is described by vector minus axial vector part, then we have W boson propagator. This is 1 over mw square, and then similarly we have the other vortex. Therefore, if you take those two into account, the couplings G and G here at the level of matrix element, this will be G square, and then you will have mw square from the propagator. This is at the level of matrix element. When you talk about matrix element square, this will become 10 power minus 10. And that is why basically it is the electron coupling with a photon and a neutrino coupling with a W boson or a Z0 boson, and then the propagator. At one place you have photon propagator, and at another place you have W or Z propagator. And that is the reason why you have a cross section which is typically 10 power minus 40 centimeter square, and here the cross section which is of the order of 10 power minus 30, 10 power minus 32 centimeter square. Now, since there was a great lecture on detectors, let me just tell you why we theorists worry about the cross section. I am just taking a simple example because I am not an experimentalist. Say when we talk about a neutrino interaction and we have a target, then we can talk about water target or iron target or lead target, which have got different densities. Now, if m is the target mass in kilogram, then the number of nucleons that will be m times 10 power 3 when we convert kilogram into gram, and then the Avogadro number. And that means if we talk about the targets, if they are nuclei, then we divide by the mass number. This is the simple picture when we talk about the target particles. Then we have this guy, which gives rise to cross section. And what is that? So this is just for students. I am sorry for the experts. If you consider a loaf of bread, and that we divide into different slices, and then particles are coming, if I have got only one slice, then the probability of interaction will be different when that particle will pass through all the slices till the end. Therefore, what I am talking about, that this density of the material is here, where I am talking about a length element dx. Rho is, say, the number of particles per unit volume. N is the number of particles which is falling on this loaf of bread. Then if the interaction is happening, then that means number of initial particles will be more than the number of final particles, because a few particles have got scattered. Say that number dn is the number of the final number of particles which have got unscattered minus the number of particles which have got incident on at the initial point of this target element. And this quantity, as scattering is taking place, this quantity will be negative because final will always be smaller than initial if you are placing some detector material. And then this change in number will be proportional to how many particles are falling on this target. And then what's the density of the target material. And that means this you generally write NF is equal to Ni exponential minus sigma times rho times X, and this sigma you call it as the cross section. Now if I talk about 1 mole of water, that is 18 grams, this contains this much molecules of water. And with this we can see the number of protons per centimeter cube or number of neutrons per centimeter cube. And this is the number with the NF is equal to Ni e to power minus sigma rho x with a typical neutrino nucleon scattering cross section that is about 10 power minus 38 centimeter square. We calculate the mean free path of the neutrino. And this mean free path is 1 over rho sigma. And this turns out to be around 10 power 14 centimeters, more than astronomical unit. And that is why the neutrinos, which are trillions of neutrinos, are passing through our body without a single interaction. And because of this mean free path, this guy is responsible for that, this sigma, the interaction cross section. Now, if we talk about neutrino electron scattering, then the neutrino electron scattering cross section is typically 10 power minus 41 centimeter square. We will see that how theoretically we obtained this number of 10 power minus 41 centimeter square. While I am telling you that neutrino nucleon scattering cross section is typically of the order of 10 power minus 38 centimeter square. And that is why you need gigantic nuclear targets. Because if you see, if I'm talking about neutrino nucleon scattering, the scattering cross section is 10 power minus 38 centimeter square. If I talk about 1 kiloton of water target, for 1 GeV neutrino, for example, volume of cubic detector of site 10 meters, this will just simple mathematics. This is 10 power 9 centimeter cube. That will hold around 10 power 32 nucleons. And therefore, when we talk about hourly event, if we have 100 neutrinos falling per centimeter square per second, we are waiting for 1 hour. This is the cross section, that is 10 power minus 38 centimeter square. This is my detector specification that we are talking about, 6 into 10 power 32 nucleons. It turns out that with 100 neutrinos falling per unit area, per unit time, for 1 kiloton of water detector, the event is only 2. Therefore, to accumulate events, you have to wait for a longer time, or you need high luminosity of neutrinos. That is why we go for accelerator experiments. Okay? In general, typically when we talk about near detector and far detector, this near detector is a convolution of neutrino nucleon scattering cross section, the flux, the selection efficiency, and detector response to the reconstructed energy. See, that is very important because we don't directly see a neutrino. What we see is an outgoing charged lepton to determine the energy of the neutrino. Now that outgoing charged lepton, if you just allow me 2 minutes, I can, since I am going to use 4 momentum transfer most of the time in these 2 talks, suppose I am talking about electron-proton scattering or neutrino-proton scattering. This has emitted a virtual photon that has got absorbed by a proton. This is elastic scattering, and we have a proton in the final state. Now say the 4 momentum carried by this electron is k, this electron is k prime, the 4 momentum of this guy, initial proton is p, and this outgoing proton is p prime. Then the 4 momentum transfer carried by this virtual photon is either I write it as k minus k prime, or equivalently I can write it as p prime minus p. Okay, and therefore, if I talk about q square, that will be equal to k square plus k prime square minus 2k dot k prime. And k square for momentum square, for electron is the mass square. And then if we say I'm talking about electron of 200 MeV or electron of 100 MeV, then mass of the electron you may neglect. In that case, you can write this guy as minus 2 prime 1 minus cosine theta. Okay, you have neglected the mass of the electron, while at the other vortex, this photon has got absorbed by the initial proton, which we say that was the final momentum of the proton will be p prime is equal to p plus q. And that means p prime square will be equal to p square plus q square plus 2p dot q. If this is elastic scattering, therefore both the sides you will get m square. Even if you deal with neutrino, if I talk about quasi-elastic scattering and ignore the mass difference between neutron and proton, which is roughly 1.3 MeV, okay, then also you have the same thing. Your q square here for the proton at rest will be minus twice m e minus e prime, because the momentum initial proton is at rest, therefore its 3 momentum is 0. Whatever you have is the energy component. Now just use these two equations. What you will find is that the energy of the outgoing electron, this will be equal to 1 plus E upon 1 plus E by m 1 minus cosine theta, where theta is the angle between the initial and the final direction of the electron. Now if you see, if this guy is a lead target, then you can always ignore this, and the energy of the outgoing particle is the same as the energy of the incoming particle. Now in general, for forward scattering angle, when theta is closer to 0, this quantity is 0, your E prime is E. But when you talk about large angle scattering, then E prime is not equal to E. For large angle scattering, E prime is less than E. And then you talk about the energy transfer, which gradually becomes larger and larger with the large angle from theta equal to 0 to 90 to 180. And therefore, when we talk about free nucleon, then we have this picture. But all the neutrino experiments are being performed using nuclear targets, where nucleons are not free. Therefore, this simple kinematics, that does not hold. Okay? Why? Because what I'm telling you, that nobody observes neutrino. You see here, what are the things? Outgoing energy of the particle, the incoming energy of the particle, and the scattering angle theta. Therefore, only two quantities are linearly independent. If you know E and theta, you know E prime. Or you know E prime and theta, you know E. In the case of neutrino, since we don't know the energy of the incoming neutrino, therefore it is E prime and theta, those are relevant to us. But the point is that those neutrons or protons, they are bound inside the nuclear target. And since neutrons and protons are strongly interacting particles, the couplings, they get modified due to strong interactions. And that is why the simple algebra that you apply to the neutrino nucleon scattering or electron nucleon scattering, when nucleon is at rest, does not hold good. Besides that, you have binding energy. Besides that, you have Fermi momentum of the nucleon inside the nucleus. Because you talk about nucleus at rest when you talk about neutrino nucleus scattering. But the nucleons in the nucleus, they are not at rest. They are constantly in motion, which we describe by the Fermi momentum. Okay? Therefore, this is the important part that these are the inputs that we talk about. Besides this guy, which is nothing but the oscillation probability. When we discuss about the accelerator experiments, as you know that there are several accelerator experiments which have been performed or those are being currently performed like NOVA, T2, K8, etc., or the future DUNE experiment. The important point is that the average energy of these accelerator experiments, they are not common. If you look at T2K experiment, if you look at the microboon experiment, then the average energy is around 600 MeV. If you look at NOVA experiment, the average energy is about 2 JeV. If you look at the DUNE experiment, the average energy is planned to be around 2.5 JeV. And there is the crisis. For example, the experiments like NOVA or experiments like where you are in the few GeV energy region. Why there is a crisis? Because in the few GeV energy region, the contribution to the cross section comes from quasi-elastic scattering, from the inelastic scattering, where you can have pion production, kaon production, eta production, associated particle production, single hyperon production, or deep elastic scattering. These are the various processes those take place. And these are the processes where nucleons are bound inside the nucleus. Therefore, if we talk about the single pion production, then we have to take into account pions final state interaction, because pions are also hadrons. And when then these pions are coming out of the nucleus, they will interact with the other nucleons which are inside the nucleus. Okay? Therefore, the final state interaction is important. And what happens because of that final state interaction of the outgoing pions? That these pions can be reabsorbed by the nucleus. These pions can change their identity, or these pions can change their energy. Therefore, the final state interaction of the mesons which are coming out, they are very important. Now, in general, when we talk about pion production, generally a delta resonant picture is given. But that is the simplest picture, because we understand delta much better than the other resonances. There are many resonances which contribute to the scattering cross section. And moreover, if we talk about eta meson production, like we have pion production dominated by delta, eta production is dominated by 1535 resonance. And that is why you have to explicitly study the property of these resonances. That is what I am telling you, that all those experiments which are being accelerator experiments or atmospheric neutrino experiments, which we talk about, shown by this dashed red region. Here, the contribution to the cross section is coming from quasi-elastic scattering, is coming from inelastic scattering, as well as is coming from deep inelastic scattering processes. And the study is important both at the nucleon level and with the nuclear medium effects. Now let me go to very basics and say I'm going back to MSc class. When we talk about electron-carbon scattering, for example, the picture I have taken here, instead of proton, I'm talking about a carbon nuclear target. Now, if I take electrons energy to be around 187 MeV and scattering angle to be 80 degree, what we find that first we see this is E prime, the energy of the outgoing electron. That means E minus E prime will give us the energy transferred to the target. Now, if the energy transferred to the target is small, we talk about the elastic scattering. And then you see here, this is the elastic scattering, and then we have the nuclear excitations. When we talk about excitations, then that means we are talking about can you excite an electron? Can you excite a muon? No, they are fundamental particles. When you are talking about resonances, you are talking about excited states. You talk about hadron spectroscopy, or when we talk about molecular spectroscopy, atomic spectroscopy. Why we talk about those spectroscopy? Because there we see the Lima and Barmer Poston series, remember from class 11. those excitations that we talk about the structure of hydrogen atom. Similarly, here also, carbon is a composite object. It's made up of nucleons, and therefore you have elastic scattering, and then you have nuclear excitations. Now further, if you increase this energy transfer, you go to this picture, you are increasing the energy transfer to the target particle, then what is happening? Your elastic scattering is getting suppressed. And what is happening? You have the quasi-elastic scattering, where the scattering is taking place with the nucleons inside the nucleus. It's not with the carbon, it is with the protons and neutrons inside the nucleus. And that is why you have this quasi-elastic scattering. Now this, I am talking about electrons of about 200 MeV. And scattering angle is 135 degrees. And therefore you see the E prime is in between 100 to 150. Where those 50 MeV have gone, those we are talking about energy transfer to the target. Now, if we talk about electron-proton scattering, and here again, if the energy transfer is very small, we have the elastic scattering. Here to bring them all on the same scale, I have divided the elastic scattering cross-section shown by the this solid line by a factor of 15. Then we have the different resonances. These resonances are again telling us that nucleons are not point particles. They are composite objects. Okay, they are not point particles, they are composite objects. And since they are composite objects, they have got a structure, they will be described by the form factors. Okay? Therefore, then we have the resonances, and finally, when the energy transfer becomes very large, in the extreme Q square becoming very high, then we say that the scattering is taking place with a quark sitting inside the proton. That is what the pure deep elastic scattering region is. When the Q square or the 4 momentum transfer square that carried by the photon, that becomes very large, then the wavelength becomes very small, and the scattering takes place with a photon with a quark inside the proton target. And that is why then we see that the results are very similar to what we have in the case of electron-muon scattering. And that is where we call it as scales. Okay? Here it shows a structure. Here we have the elastic scattering. Now this is the simplest MSc picture where we talk about electron, proton, elastic scattering, inelastic scattering, and deep elastic scattering. Okay? Now let us come to neutrinos. Since we are talking about neutrinos, therefore let us come to neutrinos. And when we are talking about neutrinos of few GeV energy region, see, I have taken 2 energy regions. One is 3 GeV and another is 7 GeV, just to demonstrate to you that what happens when we go from 3 GeV to 7 GeV. On the x-axis, we have the center of mass energy. What is this center of mass energy? This is simply, if P is the, say, initial momentum, Q is the momentum transfer, this W is P plus Q whole square. Okay? And that means when we talk about the this unit will be in GeV. Therefore, P plus Q whole square and the square root of that. This is the center of mass energy that we talk about. And therefore, you see, we start from elastic scattering, and then gradually when the energy transfer becomes large, we have high center of mass energy. And as you can see, we have first the pion production threshold, which is around 1.01 GeV. Then we have delta production threshold, which is around 1.2 GeV. Then we have eta production threshold, associated particle production threshold, and then we have finally deep elastic scattering. Therefore, if we say that this is my deep elastic scattering region, now experimentally it is impossible to directly determine the deep inelastic scattering region. Theoretically, in one of our review paper with Hore Morfin, we defined this deep elastic scattering region as W greater than 2 GeV and Q square greater than 1 GeV square. But that is not a holy number. In literature, you will find the different definition of W and Q square. But while discussing the, about DIS pure region, we took W greater than 2 GeV and Q square greater than 1 GeV square as the pure deep inelastic scattering region. But it varies from literature to literature. Now what you can see, this is the story about 3 GeV, where you have the major production from these regions, where you have pion production, delta production, and the other resonances, those contribute to these meson production. And this is what I'm going to talk about: the first resonance region, the second resonance region, and the third resonance region. In the first resonance region, we have only one resonance, and that is the delta resonance. We will see that in the second resonance region, there are 3-4 resonances. And then when we go to third resonance region, there are many resonances which contribute to the scattering cross section. Therefore, when we talk about the Dune experiment, when we talk about the precession era, then it is important that we understand this sigma neutrino nucleon scattering cross section. First at the fundamental level, when we have a free nucleon, and then at the nuclear level, when the nucleon is bound inside the nuclear target. Now this is the story at 3 GeV. When you move to 7 GeV, then you see you have the deep elastic scattering region, and then you have also the resonant production region. Therefore, that means even at 7 GeV of neutrino energies, you cannot forget about the resonance region. And that is why it is important to understand neutrino cross sections at all these center of mass energy region if we want to really understand atmospheric neutrino data or the Dune data or NOVA data very well. Now, since Uma Shankar has already taken this elementary series of lectures, and I'm going to start from the very basics, and that is the Weinberg-Slam interaction Lagrangian. Because whenever we try to obtain theoretically a cross section, since the cross section is proportional to matrix element square, because in any derivation of cross section, there are two elements. One, what we call it as the dynamical part, and another is what we call it by the name kinematic part. Okay, this dynamical part is contained in the matrix element, where we talk about the strength of the coupling, where we talk about the propagator and all that. And we have to understand this dynamical part very well. And to obtain that matrix element square, what we need is the Lagrangian for any interaction. Therefore, first you have to understand the Lagrangian before writing down the transition matrix element. Therefore, this is the general Weinberg-Slam Lagrangian, where we have the interaction with the W field or the Z field or with the electromagnetic field. Now, with this you can write down the, just looking at this, you can write down the hadronic current, where these couplings I have written down. There's no need to go into the details, though I have worked out everything in these slides to let you understand that how one proceeds or one can obtain these cross sections. If we take the example of electron-muon scattering, where what is happening, an electron emits a virtual photon that is absorbed by the muon. See, electron and proton both are point particles. Therefore, their vortex will be just E gamma mu, strength of the interaction and the nature of the interaction. Therefore, when you write the matrix element, you have the current at this vortex, you have the propagator, and then you have the current at this vortex. Now, since electron and muon both are point particles, therefore their coupling to the photon, the strength will be the same. Both are spin half Dirac particles. Therefore, the nature of the coupling will be the same. And that is why when we write the current for the leptonic part, we have U bar K prime gamma mu UK, where U is the Dirac spinor for the spin half particle. Gamma mu is telling you the nature of the interaction, which was shown by Andrew, that there are 5 bilinear covariants, and here we are talking about one of them, that is the vector interaction. And then we have the propagator, and then we have the other vertex, where you have the muonic current, U bar P prime gamma mu U. Therefore, this is how we write the matrix element once we know the Lagrangian. This is the Lagrangian for the electron interacting with the electromagnetic field. See here, just this E is outside, just these are the terms using which we are writing down the matrix element. And once we have the matrix element square, we obtain the matrix element square. Okay? And then we average over the initial spin states, because when we talk about electron muon scattering, then we know that electron and muon both are spin half particles. You can have unpolarized electron or you can have polarized electron. Now, if you are polarizing the electron, like neutrinos are always polarized. They are there, as it was pointed out in the lecture, that is spin is for neutrinos is always pointed opposite to the direction of the momentum. Left-handed, all neutrinos are left-handed, while all anti-neutrinos are right-handed, where spin is along the direction of the momentum of the particle. But for the massive particle, it can have both the polarizations. Okay, it can be left-handed as well as it can be right-handed. Therefore, if you are not applying any magnetic field, you average over the initial spin states. Okay, therefore, the important point is, just let me write here, to take the average, we take the, say, A plus B is in the initial state. We 1 upon the multiplicity of these states. If we are talking about a spin half particle, then we will have a factor of half at both these places. If I am talking about a delta, where delta is a spin 3 half particle, then I will talk about a factor of 3/2. If we talk about neutrino-nucleon scattering, then neutrinos are always polarized. Therefore, there won't be any factor here. There will be only a factor for the spin average for the nucleon. Okay, but if you talk about neutrino scattering, then there will be no spin factor. Therefore, this we have to keep in mind, that for unpolarized projectile as well as target, if they are unpolarized, we have to take a factor of half for electron and another factor of half for the muon. And then when you sum over all the final spin states, as you don't have a control on the final states, you get a trace. And this trace gives rise to an electronic tensor as well as a muonic tensor. They both are second rank tensor because this guy has to be a scalar. Therefore, since this has to be a scalar, these two are the second rank tensor. This is how we obtain the electronic tensor and the muonic tensor, and then we contract these are multiplied, and then we contract them and obtain the results in the laboratory frame when the target is at rest. Therefore, this is what you get, the transition matrix element square, average over the initial spin states and the sum over the final spin states. Now, once you have the matrix element square, then what I am telling you, that this is giving you the dynamics of the interaction, while the kinematics part, the phase space part, what momentum states are available, and the energy momentum conservation part, this is the flux part, this you take into account, and then you obtain the value of the cross section. Therefore, this is the flux factor, this delta function ensures energy momentum conservation, and this is the available phase space for the final state particles. Now, the important point is this quantity has to be Lorentz scalar. Therefore, all the components that we talk about has to be Lorentz scalar. Therefore, in general, when we talk about d cube p or d cube k prime, we say that these are the phase space available, but we divide it by E to make it Lorentz invariant. And then in our normalization, generally we talk Bjorken and Drell normalization, we take 2E particles per unit volume. That is why you have a factor of 2 everywhere. This is how one obtains the scattering cross section. Now, what happens when we go to the neutrino electron scattering? Now, what I'm telling you that when you go to neutrino electron scattering, what is going to be different is the Lagrangian of the interaction. Mind it, the Weinberg-Salam Lagrangian had 3 pieces: interaction of particle with the W field, with the Z field, and with the photon field. When we are talking about electromagnetic electron muon scattering, we discuss about the interaction with the photon field, and we took out the Lagrangian from that part. But when we are talking about neutrino electron scattering mediated by a W exchange, then we have to consider the Lagrangian from the part which is responsible for the interaction of charged particle or neutrino with the W boson. And that is why if you see a neutrino is interacting with a W field, this is the strength of the interaction, and this guy is telling you the nature of the interaction. Therefore, always it is important to write down the correct Lagrangian for any interaction. Then only you can write down the transition matrix element. Okay, therefore, this is the Lagrangian for the neutrino, whether it is nu e minus, nu mu minus, or whatever it is, this is the Lagrangian. And this is where, when we have a neutral current mediated by Z0, then the couplings get modified. Now, if I talk about inverse muon decay, which is nothing but interaction of muon type neutrino with the electron, then we have a mu minus and a nu e in the final state. This process can also only take place via a nu mu is emitting a mu minus. A nu mu is getting converted into a mu minus. That means simply we talk about a nu mu which is emitting a W plus, and it is getting converted into a mu minus, and then this W plus is getting absorbed by electron, and this electron is becoming a neutrino. This is the simple Feynman diagram for nu mu electron scattering. Now, if I talk about is Z0 exchange here, that is not possible because I cannot have a nu e here. Why I cannot have? Because we will violate lepton number conservation. Therefore, whenever we write a Feynman diagram at each vertex, we have to be careful about the individual lepton number for electron, for muon, for tauon. If there is a baryon, then we have to worry about the baryon number conservation, as well as we have to worry about the charge conservation. These 3 are the important factors when we write any vortex. What are these factors? One is electron lepton number, muon lepton number, and tauon lepton number should be independently conserved. Then baryon, if there are baryons, baryon number has to be conserved, and if there are charged particles, then the total charge has to be conserved. And that is why you see the total charge arriving at this junction was 0. Total charge leaving from this junction is W plus is getting emitted, and it is getting converted into a mu minus. Therefore, the total charge here in the final state is 0. While plus 1 charge is coming, it is getting absorbed by electron, which has got a negative charge. Therefore, plus 1 charge and negative charge is giving me a neutral particle in the final state. While we have to keep in mind that electron lepton number is plus 1 for this, and electron lepton number is plus 1 for the other one. Therefore, when we write down the Lagrangian, we have to keep in mind, and with that, we write down the transition matrix element. Here you see, again, we have this part, Besides that, we have the propagator. Therefore, rule of thumb, whether we are talking about electron-muon scattering or neutrino-electron scattering or whatever is there, the rule of thumb is that first you have to get the Lagrangian of the interaction, and then you write down the transition matrix element. Now, once you have the transition matrix element, then the next task will be to obtain the matrix element square. Again, you average over the initial spin states and sum over the final spin states, and you obtain with the same prescription as that one does for electron-muon scattering, one can obtain the differential scattering cross. Now this is, see, here I have taken mu and electron in the initial state, and I have mu minus and neutrino in the final state. What happens instead of mu if I talk about electron here? What will happen if I have an electron type neutrino and electron in the initial state, and electron type neutrino and electron in the final state? That means I am talking about nu E scattering. I have electron type neutrino and electron in the initial state, and electron type neutrino and electron in the final state. Now this process will take place via W exchange as well as Z exchange. Why? Because a nu E can emit a W plus and get converted into an electron, and that W plus will absorb by electron and it will get converted into a nu E. But at the same time, we can have another diagram where a nu E emits a Z0, it remains as Z0, a neutral particle, and that Z0 gets absorbed by electron and you have an electron in the final state. Therefore, when we talk about why I took this interaction first, because this was only possible via W exchange. But when we talk about the other exchange, similarly you can have nu mu electron scattering, that is only possible via Z0 exchange, or when we talk about nu E electron scattering, this takes place via charge current interaction as well as via neutral current interaction, and that means the Lagrangian for these two will be different because the strength of the coupling is different. Mass of W boson is not the same as the mass of Z0 boson, but when you write the total matrix element, that will be the sum of the matrix element from this term diagram as well as sum of the matrix element from the other diagram. And that is why you have the Lagrangian independently for these three vortices, a neutrino interacting with a W field, an electron interacting with a Z field, or a nu E interacting with a Z field. Just those three pieces of Weinberg-Slam Lagrangian using, again I am collecting those three terms here. And once I have those three terms, I can write down the matrix element, and using them, we can obtain the scattering cross-section. Therefore, this is how we obtain the scattering cross-section for the particles which have not got structure. These are the matrix element or the cross-sections for the processes where the particles which are involved are elementary particles. Electron, muon, tauon, electron type neutrino, muon type neutrino, etc. Though the mediated particles are, it can be a photon, it can be a W boson, or it can be a Z0 boson. But what happens when we talk about electron-proton scattering or neutrino-nucleon scattering? Then in that case, proton is not a fundamental particle. It has got a structure. And then form factors come into play. Okay? Therefore, when we talk about electron-proton elastic scattering, that means electron-proton in the initial state and electron-proton in the final state, we write down the matrix element. Here, this gamma mu is just telling you that since this is a vector interaction, because this part has not changed, only this part is changed. This is a vector interaction, therefore this interaction has to be on also a vector in nature. Otherwise, you won't get a Lorentz scalar. And therefore, but what is that gamma mu? That we don't know. Okay, what is that structure? complete structure that we don't know, that just we know that it should be a vector interaction in nature. Now, how we proceed? We write down all the 4 vectors, those are available to our disposal. These 4 vectors, as you can know, at this vortex, this is the incoming proton, this is the outgoing proton, and this is the momentum transfer. Therefore, this 4 vector can be P and Q. This 4 vector can be Q and P prime, or P and P prime. Or if I write in terms of the 4 momentum transfer as P prime minus P, therefore it can be P mu and Q mu, then also you will be able to know P prime. Or even it can be P prime minus P and P prime plus P, difference of the momenta and the sum of the 4 momenta. Therefore, there is no rule of thumb that you have to start from P mu prime, or Q mu P mu prime, or whatever it is. You can start with the difference of the 4 momenta as well as the sum of the 4 momenta. And then you have the 5 bilinear covariants available at your disposal. But keep in mind, when we are talking about electron-proton scattering, then this is an electromagnetic interaction where parity is concerned. Okay? Therefore, when we write down the vector current, we have the 5 different terms in general. This is the basic vortex that we are talking about. And these A, B, C, D, E, they are scalar functions. Okay? And using current conservation and Gaussian decomposition, what we come across that instead of these 5 scalar functions, ultimately we come down to only 2 scalar functions. And those 2 scalar functions are recursioned as F1 and F2 structure functions. One is known as Dirac form factor and another is known as polyform factor, Dirac and polyform factors. Therefore, we have the general structure. Again, you see, this is the vector interaction. We have a gamma mu, besides that we have F1 plus F2, and then we have a P mu, which is the sum of the 4 momenta upon twice M F2Q square. Therefore, this vortex, protonic vortex, has a term which is something like this. Now, again, we go back to the point that this is my hadronic current, where we have, which is vector in nature. We write down the matrix element square. Here also we have the leptonic tensor and the other tensor. Now we call it by the name hadronic tensor because we are talking about proton. We are talking, similarly we talk about neutron or pion or kaon. These are all particles which have got a structure. They are described by the form factors. Therefore, the important point is we again write down the hadronic tensor. We have the leptonic tensor. We contract them and contract them to obtain the results for the differential scattering cross section. Okay, this is what in literature is known as Rosenblatt cross-sectional formula for the electron-proton elastic scattering. Okay. Now, similarly, we go to the neutrino-nucleon scattering. When we go to neutrino-nucleon scattering, what is the difference? There are 2 differences. One is we are now talking about neutrinos, where parity is violated. We are talking about neutrinos, weak interaction, which is described by V minus A type of interaction. Vector as well as axial vector. Therefore, in principle, again, we start from the same point. We talk about the leptonic part, which has the V minus A structure, and the hadronic part, again, which has got a V minus A structure. But because of parity violation, we have an additional term. And like previously we had F1, F2 and F3, here we have G1, G2, G3. Then we apply current conservation, time reversal invariance, etc. To obtain the results for the general result for the hadronic current. Okay, let me stop here. I will start from this point that we have the neutrino-nucleon scattering, and and then how to write from here the expression for the matrix element square. What are the subtleties that one should take into account in obtaining the expression for the differential scattering cross section? Because see, when we will talk about this, we will talk about the form factors F1, F2, etc. We will say that we are going to use the form factors which have been determined from the electromagnetic interaction. I will talk about it tomorrow, that from where we will take the electromagnetic interaction part, then we will have this G1 and G2 part. This is known as axial form factor and this is known as pseudo-scalar form factor. Now, this axial form factor has a structure G1Q square. Generally, that is taken to be a dipole form. And there you will see that there is an uncertainty in determining the axial dipole mass. And that is in debate since the mini-bone experiment, since 2008, 2009, that what should be the value of axial dipole mass. In literature, if you will see, the world average value for this axial dipole mass is 1 GeV, 1.0102 GeV. While if you look at K2K experiment, T2K experiment, Minerva experiment, and many other experiments, it has varied by 20 to 25%. 1.2 is the recommended value somewhere in the experiment. In some theory, the recommendation is for 1.3. But what we see that if you evaluate the neutrino cross sections with for 1 GeV, simply 1 GeV neutrino with Ma equal to 1 GeV and Ma equal to 1.2 GeV, 20% change in the axial dipole mass brings a 20% change in the cross section. And that is why it is important to determine the value of axial dipole mass. Generally, this value is taken from the almost 40 years ago, the experiments were performed at ANL and BNL, and there the uncertainties are large. This value is taken from there, but it has been emphasized by us that before going ahead, it is important to perform first the experiments with deuteron targets to determine this value of axial dipole mass at the nucleon level, and then go to the neutrino nucleus interaction part. Okay, we shall talk about this tomorrow. Thank you very much.
So we have a couple of quick questions. Otherwise, you will go for lunch.
When we talk about these form factors, these are basically neutrino nucleon form factors. In general, the neutrino nucleus form factors would be different. So how?
No, see, in the electron scattering experiment with that, we can determine that. But for there is nothing like neutrino nuclear form factor for neutrino scattering experiments. Okay, what we do, the basic input that we take is at the nucleon level. Then we take the nuclear medium effects and evaluate the cross sections with nuclear medium effects. That is a challenge in the neutrino nucleus scattering experiments. Okay, because here you have additional contribution from the axial vector part, and that cannot be determined directly. While if you see, I have not gone into the details, when we talk about those electromagnetic form factors, those Fp and Fn, they are described in terms of the experimentally determined electric and magnetic Sachs form factors. And these electric and magnetic Sachs form factors, those have been determined from electromagnetic interaction processes. And most of the time, one takes the dipole form, though the deviations from dipole have been observed. And that is why if you look at the literature, I have mentioned somewhere here, there are many parameterizations for the electric and magnetic Sachs form factors. But generally today in neutrino physics, most of the time calculations are performed with a BBA05 form factors. But here the uncertainties are less. When we go to the neutrino experiments where axial part contributes, the uncertainty becomes large. But the vector part of the weak current, that is fixed by this electric and magnetic Sachs form.
So I was a bit worried, like the nucleon is not the same as a nucleus, right?
Yes,
so
sure.
When we parameterize the matrix elements of a nucleus and a neutron, then the form factors
will change.
Will change.
Will change. For sure they will change. And tomorrow I'm going to talk about it, that what happens when you take into account nucleon correlation effects. And in fact, in quenching in beta decay is a well-established phenomena almost since last 40 years, 50 years, that these gets suppressed when you talk about, and the suppression is about 25 to 30%. Yes. Is there any water? Is public?
Hello. So my
Using? They are in debate, not at the purpose. We have discussions in SNOMAS and at the new estate board and everywhere else. But who? What's the energy range? You are talking about Dune. Yeah, you are talking about, but Dune is another 6, 7, 8 years. But it's expected that their deuterium target will be used. No, not at all, not at all. See, tomorrow I will talk about the different things, that what are the uncertainties at the nucleon level. See, nuclear medium effects uncertainties are quite different than the uncertainties at the nucleon level. At the nucleon level, we have to fix the couplings, the Q square dependence, etc. And then when you will go and put it in the nucleus, you will be sure about the facts that you know many things about the nucleons. It is only the nuclear medium effects that you don't understand. But doing the measurements in deuteron will not tell you anything about the medium effects in argon, for example, which will be used by Dune collaboration, because deuterium effects are entirely different. Nuclear medium in deuterium is entirely different than what it will be in argon. It will fix the things at the nucleon level.
Okay, so if there are no more questions, okay, you have one more, okay. Yeah. Can you just wait?
So you said that
It's working. Not nuclear form factors. So you mind it.
the nucleon.
I'm talking about nucleon.
Nucleon form.
Nucleon, yes. I am talking about at the nucleon level. There are two things. First is that you have to understand quasi-elastic scattering at the nucleon level. You have to understand pion production, kaon production, etc. The inelastic scattering processes at the nucleon level. What I am telling you, that there are several resonances, those contribute to the scattering cross section. Now, I will show it to you tomorrow. I don't know how much time will I get. That if you talk about single pion production, there are 8 or 9 resonances, those contribute to the cross sections. You talk about eta production, there are many resonances. Similarly, for associated particle production, there are 7, 8 resonances. Now, when you talk about the resonances, then you have to talk about nucleon to resonance transition form factor. Now, when you talk about nucleon to resonance transition form factor, there also it has got VA structure, V minus A structure. You have the vector part and you have the axial vector part. The vector part is determined from the helicity amplitudes. But the helicity amplitudes, they are well determined only for a few resonances. They are not determined very well for all the resonances. Therefore, there is an additional uncertainty in the resonance sector from the vector part also. And then entirely the axial vector part we take in an ad hoc way, except for a few resonances. That is why I am telling you that at the nucleon level, first we have to understand this neutrino-nucleon cross section from a few hundreds of MeV to few GeV range. You know, when we had started almost 14, 15 years ago, the neutrino-nucleon deep elastic scattering cross sections studies. There we were told that don't worry about nuclear medium effects in the DIS region. We showed them that no, nuclear medium effects in this few GeV energy region, in few Q square GeV square region is again very important. Now, if you look at the DIS data of Minerva experiment, you will find that none of the Monte Carlos are able to explain the experimental data. And that means even in the DIS, where we understand that nuclear medium effects will be very small, we don't understand. Therefore, there is both. We need understanding at the nucleon level and we need understanding at the nuclear level. If you look at the nu-tau nucleon deep elastic scattering, for example, ice cube experiment and others who are talking about deep elastic scattering experiments and all that, you will find that even at the nucleon level for nu-tau nucleon DIS, the uncertainty is about 20 to 25% in the different theoretical calculations. And that means even in the DIS region, things are clear for electron type neutrino and muon type neutrino at the nucleon level, but for the tau neutrino case, where additional form factors come into play, structure functions, we don't understand very well the things at the nucleon level. Then we have to go to the nucleus. Therefore, there are problems presently, currently at the nucleon level also, which we have to fix. Then we have to go to the nuclear level. It's the problem of getting hydrogen. The problem is of getting theorists are trying hard to have the experimentalist hydrogen and deuterium targets. But for the experimentalist, it is very difficult to convince the government that we can have hydrogen or deuterium targets because of security issues.